we're going to do an example for MCMC, and we're going to use, again, the icing model. So recall, this is our icing model that we're going to use for example, image denoising. And recall that in our icing model, we have one variable per pixel, and we have potentials for neighboring pairs of variables, where the potential equals x of j times xs times xt. That is, this will be positive if they're the same and negative if they're different, times some value j. So let's derive our MCMC algorithm. So first thing we need to do is we need to pick a proposal distribution. And for our proposal distribution, we're just going to, at each step, we're going to pick one xi at random, and we're going to flip it. That means the only thing we need to do is we need to calculate our acceptance probability. Okay, let's see what that's going to be. Our acceptance probability we know is this thing, p x prime over x. That is the ratio of the probabilities of our two values times q of x given x prime over q of x prime given x. So that is the ratio of probabilities that we would go from x prime to x versus from x to x prime. So first thing, if we look at this factor, we can see that our proposal distribution is symmetric. That is, there's an equal chance that we choose x prime to flip to, or sorry, we choose xi to flip if it's 1 and versus 0. So whatever the value of xi is, there's an equal chance that we choose to flip it. So our ratio is symmetric. So this thing equals 1. That means we just have to focus on this factor here. Okay, so let's see what this factor is. So all we have to do is we have to look at our probability for x prime and x. So note that the only things that are gonna change when we flip, for example, x8, is the factors that involve x8. So the factors for these 4 edges here are going to change. Everything else is going to be the same. So we only need to pay attention to those values. That is, we're going to have a bunch of stuff here on both top and bottom. There'll be some factors that don't involve xi, and therefore they're going to be the same. So they're going to cancel out. So that's why we don't need to pay attention to them. So let's look at just the factors that involve xi. Those are going to be the following. J in the neighbors of I. Let's make clear that that's an I there. So that's just a way of writing, if it's x8 that's changed, that's going to be 3, 7, 9, and 13. And, okay, so we need to divide the x prime value by the x value. So that's going to be x of j xi prime xj. Xi prime is the flipped version of xi. And on the bottom, we have the same thing. I'm not going to write out the bottom here. It's just the same product. Jxi not prime xj. Okay, so this thing is this term here. By the way, I should add that we have also a 1 over z in both cases, because recall that p is unnormalized, or rather, if we just multiply together all of our factors, we get an unnormalized probability. So we have to add in our partition function to normalize it, but that's also on the top and bottom, so we can also get rid of that. Okay, so let's keep going. Notice that we have the same product on the top and bottom here, and it's a whole bunch of exps. So we can pull the exp out front, and the product turns to a sum. Then the second thing to notice is there's kind of two cases. Let's look at the case where xi and xj match. Then this thing is going to be 1, and this thing is going to be -1. So when we take, we have a -1 here divided by x with a 1, we're going to get a -2 here. Vice versa, if xi and xj mismatch, this is going to be a -1, this is going to be a +1. We're going to have +1 minus -1, that's going to be 2. So what we're going to end up getting is just 2 times xi xj. Notice that we don't need to anymore 2 minus xi xj. Notice that xi prime xj is just -1 times xi xj. So equivalently, we could have written this as no minus sign positive 2 xi prime xj. That's an equivalent way to write this. And actually, let's take the 2 and put it out front. We can simplify this a bit further. This sum here, if we think about it, this is just the increase in matches, right? Because we have, for each case where we went from not matching to matching, we get a +1 in here. For each case where we went from matching to not matching, we get a -1. So this is going to be the increase in matches. And then there's some constant factor here, and that goes through an exp. So if the increase in matches is greater than 0, if we have a positive increase in matches, exp of that positive number is going to be greater than 1, meaning our accept probability is going to be 1. So we're always going to accept moves that increase our number of matches. If we decrease the number of matches, that's going to be exp of a constant times a negative number. So this whole thing is going to be negative. So we're going to get a number between 0 and 1. And that is, we're going to get some probability that's less than 1 of accepting. And the probability, what the probability is going to depend on how big the decrease in matches is. If we get -4 matches, that is, we're flipping from all matching to no matching, then this is going to be a big negative number, and we're going to get a very low accept probability. If it's just 1 decrease in match, then it's going to be a relatively large probability, still less than 1. By the way, if this is 0, that is, we neither increased nor decreased. We exactly kept the number of matches the same. This thing is going to be 0, and our accept probability is going to be 1 still. Okay, and that's very intuitive. That is, we accept moves that increase our matches. If it's a move that decreases our matches, we accept it sometimes. And notably, our probability of accepting depends on the strength of the pairs, which is controlled by this parameter j. So if j is very large, that means we think that every pair really, really needs to have the same value. If j is small, then we don't care so much. And so if j is very high, we accept fewer changes that decrease our number of matches.